start recording here. And today, so what have we done so far? We've done a lot. We've done a lot of factoring, especially with rational expressions. We know how to add, subtract, multiply, divide them. We know how to simplify complex fractions. We know how to solve rational equations. We know how to factor all the different kinds of factoring scenarios with different trinomials, perfect square trinomials, difference of perfect squares, sum and difference of cubes, perfect cubes. What else do we do? We did a system of equations. So we covered a lot up until this point. Okay, so today we're going to continue with more algebra stuff. In particular, we're going to be talking about rational exponents. So we've dealt with a lot of exponential expressions, right? We know how to take certain exponential expressions and raise them to certain powers. And we know how to deal with negative exponents. But now we'll be dealing with fractional exponents or rational. So the word rational means fractional or fraction, right? Because ratio is in it. So now what happens when we have fraction as our exponents? Okay, so let me give you an example. What if I have 27 raised to 2/3? How do I evaluate 27 raised to 2/3? So one thing I could do is I can rewrite the power. And how would I do that? Actually, I'm not going to do that first. Actually, what I'm going to do is I'm going to rewrite 27 as a power of 3. So look what happens when I rewrite 27. Isn't 27 3 cubed? So then I can rewrite 27 as 3 cubed to the 2/3. And now what do we know about powers of exponents? When you multiply exponents, when you have a power raised to a power, you have to multiply the exponents. So what do I get? I get 3 times 3 raised to the 3 multiplied by 2/3. Do you see that? So I multiply 3 and 2/3. And when I do so, the 3's here cancel, and I'm left with 3 squared. And 3 squared equals 9. So for this step, I rewrote the base as a power of 3. But maybe you didn't know that. Maybe you didn't know that directly, right? So there's a connection that exists between rational exponents and radical expression. So we're going to be dealing with radicals a lot more from now on. And we're going to see how they connect with rational exponents. So this is just a little introduction here. So one thing I want to talk about is when you have, for example, 4 to the 1/2 power. I'm taking 4 and I'm raising it to the 1/2 power. Another way I can write this is the square root of 4. And I know that's 2. So what's the rule here? What's the rule? The rule is that when you take x, any base, and you raise it to the 1/2 power, that's equivalent to taking the square root. So the connection between raising to the 1/2 with the fractional exponent and the radical expression is that it's taking the square root. So that's an important rule that we must remember. Now, what if we have something like this instead? What if we have, let's see, what if I have 125 raised to the 1/3 instead power? Then what's the radical for this? The radical will be rewritten in this way. So raised to the 1/2 power, and you're taking the what? Square root, right? Square root. If you raise it to the 1/3 power, you're not going to be considering the cube root. So x to the 1/3 is actually the cube root. And the cube root is very similar to the square root. What does the square root say? The square root says, hey, what number when you square it gives you 4? That's 2. In this case, if I say the cube root of 125, I'm asking for what's the number when I cube it, raised to the 3rd power? What number raised to the third power gives me 125? And that equals 5. And in reality, there should be a 2 here. But because we use the square root so much, we just omit it. If you see the square root, you should know that there's a 2 here, and that 2 corresponds to that 2 in the denominator of the fractional exponent. The same way that 3 corresponds to that 3 in the denominator. And then we can keep going with this, right? We can say, for example, what's 16 to the 1/4 power? That's equivalent to saying, what is the 4th root of 16? Or it's equivalent to asking, what number raised to the 4th power gives me 16? And that would be 2. So then what's the rule here? X to the 1/4 is equal to the 4th root of x. So this is the 4th root. And we keep on doing this, right? To the 5th root, 6th root, 7th root, right? So what's the general rule for these fractional exponents? What's the general rule then? The general rule is that if you take x and you raise it to the 1/n power, this is the same thing as taking the nth root of x. So this is the nth root. Okay? So slowly we're making the connection between fractional exponents and radical expressions. So another little example here. What is 32 raised to the 1/5 power? Well, that's equivalent to saying what? The 5th root of 32. And can anybody tell me what number raised to the 5th power gives me 32? What number, when you multiply it to itself 5 times, gives me 32? It's a small number. It's a single digit. 2. That is right, guys. 2. So the fifth root of 32 is 2. Okay, but going back to the example that we started with, we don't always have fractions that only have a 1 in the numerator. So what happens when we have a fraction that has a number other than 1 in the numerator? How do we take care of that? So let's go back to our example that we started with, right? We said, what is 27 to the 2/3? What is that? What is that? So what I'm going to do is, this is what I started with, right? I said, let's rewrite the exponent this time. I know we started with rewriting the base, but let's rewrite the exponent. And what do I mean by that? Well, I say now I can rewrite this as 27 to the 1/3 multiplied by 2, can I? 1/3 times 2 is 2/3. And then I can do something further. I can rewrite this as 27 to the 1/3 raised to the second power, because when you multiply exponents, you have them as a power raised to a power. So I can rewrite it this way. But I know what's 27 to the 1/3 power, right? Isn't this the same thing as the third root of 27? And this entire thing being squared? And what is the cube root of 27? It's 3. And I'm squaring that, which is 9, which is exactly what I got in the beginning. I got 9. But you see how I get it now? So what did I really do? I rewrote the exponents in such a way that I can get this radical appearing out of nowhere, seemingly. But it didn't just appear out of nowhere, because that 1/3, because of that denominator, is a 3. So I know my radical has that 3 in the outside, and this number, I should have said something. This represents the radical. This is the index of the radical. It tells me what kind of radical it is. So the denominator tells me the kind of radical. So if it's a 3, then it's a cube root. If it's a 4, it's a fourth root. 5, it's a fifth root. If it's a 2, it's a square root. So that number in the denominator tells me the type of radical that I'm dealing with. So then what's a rule that we can figure out from here? So if I have x as my base, and I have an exponent, m over n, then I can rewrite this as a radical expression by taking the nth root of x and raising this to the mth power. So I can do this. This is one rule. And let me think of another one. Now, what if I get this? Let's say I have 8 to the 2/3, right? And I'm going to do the exact same thing. I'm going to rewrite the exponent, but I'm going to rewrite it slightly differently. I'm going to rewrite it as 2 multiplied by 1/3. So the order here, I'm going to change it. Instead of writing 1/3 times 2, I'm writing it as 2 times 1/3. And now look what I can do as well. I can write this as what? 8 squared raised to the 1/3 power. I can also write it that way. And the 1/3, what does the 1/3 mean? The cube root of 8 squared. And 8 squared is what? 64. And the cube root of 64 is 4. I could have also done it differently, right? I could have written it as 8 to the 1/3 squared. This equals the cube root of 8 squared. The cube root of 8 is 2 squared equals 4. Do you see how I get the same thing? But I interchanged the order of the multiplication, and that gave me two different variations of the same solution. So what's another rule? So I should extend this rule now. Not only can I write the m over n as the nth root after, the nth root first and then the mth root, the mth power, I can also write this as the nth root of x to the mth power. I know this sounds kind of weird to say that. The nth root and the mth power. Whoops. You know what? Let me just erase this. Create a new one altogether. So this is my final rule here. And this connects fractional exponents with radical expressions. So let me give you an example. 16 3/4. How can I rewrite this? I can write it in two different ways, right? I can write it as the fourth root of 16 cubed, or the second way is I can write it as the fourth root of 16 first, then to the third power. Which one do you think is more convenient? Is it the first way or the second way? One or two? Or in other words, which one is easier to do? Is it easier to do number two, taking the fourth root first, then cubing it? Or is it easier to cube 16 first and then taking the fourth root of that? One is easier. Really, Jalen? How come? What makes one easier? Isn't 16 cubed a really big number? What is 16 cubed? 16 cubed is 4,096. Now, does anybody know the fourth root of 4,096 off the top of their heads? Yeah, so it's okay. You see that sometimes there are other more convenient ways to do the same operation. So you start to see that, well, you know what? 16 cubed is way too big to take the fourth root of it. But you know what's easier to take the fourth root of? 16. And what is 16? The fourth root of 16. Isn't it 2? So the inside here is actually easier to do. I get 2. And what is 2 cubed? 8. And if you put the fourth root of 4,096 in your calculator, you would get 8. But do you see how this one here is hard to do without calculator? And this is easy without calculator. So you don't need a calculator if you know the easy part, if you know the easy way. Okay? I know I haven't mixed in this yet, but what happens when I have a negative fraction? Uh-oh. Now we got our worst nightmare, don't we? We got not just a fractional exponent, but we have a negative one at that. So how do we take care of negative fractional exponents? What's the first thing you have to do? How do you take care of that negative? I don't want negative, right? I like positive
Um,
exponents. So then what must I do?
you put it as 1 over 32 to the power of 3 over 5.
Perfect. Thank you. That is right. You just put it in the denominator and put a 1 on the numerator. Now I have to make sure I have to take care of this, right? I have to take care of the denominator. Now 32 to the 3 halves, to the 3 fifths, I have to rewrite it as a radical expression. And I can take the fifth root of 32 first and then cube it. Because it's easier to take the fifth root of something and then cube it rather than taking 32 cubed and then finding the fifth root of that. That's a lot more work. So the fifth root of 32 we've seen already is 2. And we have to cube 2. And you get 1 over 8. So taking care of negative fractions, not that bad. Just make sure you make it positive, and once you have it positive, then you'd use the radical expression to find your answer. Okay. Let's do some more, shall we? So what if I have a to the 1/2 power multiplied by a to the 2/3 power multiplied by a to the negative 1/4 power? I want to simplify. Of course, our whole life in Math 115 is simplify, simplify, simplify everything. And what I mean by simplify is I want to get a with one single base and with one single exponent. That's it. So what I have to figure out is the exponent. But what do I know about multiplying exponential expressions using the same base? What happens when I multiply with the same base? When you multiply by the same base, what happens with the exponents? We add. Very good, Sima. Yes. We take all of these little exponents and we add them. So we have to add them. So it's going to be a and then parentheses. We got 1/2 plus 1/3 minus 1/4. So why don't we do that separately? So what's 1/2 plus 1/3 minus 1/4? How do you add fractions? I can't just add them like this. I need to have the common denominator. So what's the common denominator? Or the LCD as you call it. What's the LCD of 2, 3, and 4? Does anybody know the least common denominator? 12. Very good. So this is 12, so I must make all the denominators 12, so I must multiply everything accordingly by the appropriate factor that gives me 12 in the denominator. So 4 is the one for this guy, and then we got 3, right? So then when you multiply them out, what do you get? You get 6 over 12 plus 4 over 12 minus 3 over 12. And then you have the same denominator, leave the denominator alone, combine the numerators. 6 plus 4 is 10, minus 3 is 7, 7/12. And this results in a to the 7 over 12. So we have to become very, very comfortable with fractions, knowing how to subtract them, knowing how to add them, knowing how to multiply, knowing how to divide them. We have to become comfortable with fractions for this. Okay. Next example. What if I got something like this? X to the 6, y to the 4th, and I raise that to the 3 halves. What happens here? My bases are not the same, so I can't combine the exponents. But both of these exponents are raised to the same power. Because of that, I can take x to the 6, raise that to the 3 halves, multiply that by y to the 4th, raise that to the 3 halves as well. So I can take each thing into parentheses and raise it to the corresponding same exponent. And then these exponents here are being multiplied to one another. So I get x to the 6 times 3 halves times y to the 4 times 3 halves. 6 times 3 halves, the 2 goes into the 6 3 times, so 3 times 3 is 9. The 2 goes into the 4 2 times, and then you get 2 times 3 is 6. And this is my final answer. So x to the 6 times y to the 4th quantity, the whole thing raised to the 3 halves, is equal to x to the 9 times y to the 6. I'm applying the same rules of exponents. It's just that now they're fractions. That's all. Nothing necessarily major that's completely new. It's just that now our fractions are also, our exponents are also fractions. Okay, and let's simplify one more of these guys. So this is the one that everyone likes, right? Things that look like this. So 8a cubed b to the negative 4. Divide that by 64 a to the negative 9 b squared. Parentheses, raise that now to the 2/3. Whoa. Now I have this fractional exponent out there instead of having just a regular whole number or an integer. What do I do? I still take care of it the way I normally would, right? Again, there's many ways to go about this, but I believe the simplest way is to take care of the inside first. Take care of everything inside the parentheses first. So I'm going to take care of everything inside here first. So let me see what I can simplify. I notice that the 8 and the 64, right, they cancel. The 8 cancels or divides the 64 8 times. So I'm going to have an 8 in the denominator. Now, what I'm going to do is I'm going to quickly make these negative exponents positive by moving in their corresponding places that make them positive. So if you're in the numerator, you want to become a positive exponent, you go into the denominator. If you're in the denominator and have a negative exponent, move it to the numerator. So when I do that little switcheroo there, I get a cubed times a to the 9th, and I get b squared times b to the 4th. This is still raised to the 2/3 power. Now that I have in the numerator two bases that are the same, I just add the exponent. So 3 plus 9 is 12. So I get a to the 12th power. Divide that by 8. B squared times b to the 4th. I add 2 and 4 together, and I get b to the 6th. And again, this is still raised to 2/3. So I still haven't taken care of the 2/3 yet. All I've done is simplify the inside expression of the within the parentheses. And then now I can rewrite this as a to the 12th raised to the 2/3. I can write this as 8 to the 2/3 and b 6 to the 2/3. I can do all of this. Right? And now what do I do? Multiply. Multiply. And then what is this? 8 to the 2/3. Let's do that real quick. What is 8 to the 2/3? Isn't this the cube root of 8? squared. Isn't the cube root of 8 2? And squaring that gives me 4. So don't I get 4 in the denominator? Now I have to multiply 12 times 2/3. What is 12 times 2/3? 3 goes into 12 4 times. 4 times 2 is 8. Isn't this 8a to the 8th power? And then isn't the denominator 6 times 2/3? 3 goes into 6 2 times. 2 times 2 is 4. So isn't this b to the 4th power? So isn't my answer 8 to the 8th power over 4 times b to the 4th power? So that's how we simplify these exponential expressions with this given fractional exponent. So we shouldn't be afraid of fractional exponents any further. Okay. Now we're going to enter into a very interesting portion of this. Hold on one second. Okay. So now we have that. Now I want to simplify radicals. With variable expressions, with powers of variables. This is where things can get a bit tricky. So hopefully up to this point, it's okay. So for example, if I take the 5th root of 243, x to the 5th, y to the 15th. Let's say I want to simplify this. One thing I can do is I can rewrite it as a exponent, right? I can rewrite it as 243 x to the 5th times y to the 15th. This entire thing is being raised to the 1/5 power. And when I have it this way, I can also rewrite it as 243 1/5 power times x to the 5th 1/5 power times y to the 15th to the 1/5 power. But what I really just did was I rewrote this, right, as the 5th root. I can rewrite this as the 5th root of 243. And the 5th root of 243 is it's 3 to the 3 to the 5th power is 243. So 243, the 5th root of 243 is 3. And then what happens with these exponents? Aren't they multiplied? So 5 times the 5th is what? X to the 1st power, because 5 times 1/5 is 5 over 5. And then 5 times 1/5 is 15 over 5. Which, so then the answer will be 3xy squared. So we have these situations where we can simplify very, very nicely. So another little example, the cube root of 8 x to the 12th y cubed. Same idea. I'm going to rewrite it as an exponential with a fractional exponent. So this becomes 8x12 to the 12th power y cubed to the 1/3 power. I take everything individually and raise it to the 1/3 power. And the 8 to the 1/3 power, the expression, can be rewritten as the cube root of 8, which is just 2. So I know that's going to be 2. And then what else do I know? The exponents are being multiplied to one another. So this is x times raised to 12 times 1/3 times y 3 times 1/3. 12 times 1/3 is 4. Y cubed times 1/3 is y to the first power. And that's it. Okay? So again, we're going back and forth with this. We're going back and forth with radical expressions, fractional exponents, radical expressions. We should be able to go back and forth at any moment. Now, before we continue, though, there's one thing I need to make mention. So this is an important note here. And I'm going to start with an example. Does anybody know the square root of -4? And does anybody know the cube root of -8? And I can rewrite this as -4 to the 1/2 power, and I can rewrite this as -8 to the 1/3 power. So what is this equal to? And what is this equal to? Well, we know the square root of 4 is 2, right? But what's the square root of -4? What number, when you square it, gives me a negative number? What number, when you cube it, gives me a -8? Can anybody give me a number? So the thing is, actually, the square root of -4 is a trick question. Maybe not such a trick question. It has two answers. The square root of -4 for us in this class has no real answer. There's no real number. There's no such thing as taking a number and squaring it and getting a negative number. Even if you have a negative number to start with, right? Even if you have -2, for example, and you square it, -2 squared is +4. So it's impossible to get a real number and square it to get a negative number. There is no way to multiply anything to itself to get -4. Henceforth, the square root of -4 is not real. It's not real. But then we can talk about complex numbers. The square root of -1 is I, and that's another thing entirely. So then we can actually find it. It's just not going to be in the real world. It's going to be in the complex world. However, the cube root of -8 is actually -2. Why is that? Negative 2 cubed is actually negative 2 multiplied by negative 2 multiplied by negative 2. When you multiply a negative with the negative, you get positive. 4 times negative 2 is what? Negative 8. So then what do I take away from this? If I have an even radical, the index of the radical, so if the index of radical is an even number, then oh yeah, so one thing I forgot to mention is that the thing underneath the radical is called the radicand. So the radicand is the expression under the radical. So whatever that is, it could be all of these guys, right? This is a radicand, and this is the radical. This is the radicand, and this is the radical. So then the radicand cannot be a negative number and will result in uh, a with no real answer, with no real number as the answer. But if the index of radical is an odd number, then there is a real number for a negative radicand. So if I take, for example, the fifth root of negative 32, that's going to be equal to negative 2. If I take the fourth, if I take the third root of negative 27, I get negative 3 because negative 3 cubed is negative 27. Negative 2 to the fifth power is negative 32. However, so these are like little further examples here. However, if I take the fourth root of negative 64, not real. If I take the eighth root of negative 256, not real. If I take the square root of negative 100, not real. So even radicals, if I have a negative underneath the radical, I don't have a real number for it. If I have an odd radical index of a radical for a negative number, then the number exists and it's a real number and it's a negative number. So I just want to make sure that is established as well. Okay? Okay. So slowly we start to see that there's a general rule for multiplication. So there's a general multiplication rule for radicals. And the general radical rule for radicals is if I have the nth root of a product, then I can rewrite this as the nth root of one of them multiplied by the nth root of the other. And we've been noticing this in some of our work that we've done. We just split up the radicals whenever you multiply them. It's only under multiplication, not with addition. So now I want to simplify radicals when radicand is not when a radicand is not a perfect square. Whoa. Nor a perfect cube. Dot, dot, dot. Nor a perfect to the fourth power to the fifth power. So whenever we have things that are not perfect squares, so as an example, right? For example, the square root of 50. 50 is not a perfect square. But I still can simplify it. How do I simplify such a thing? I need to figure out if there is any factor. So find the largest perfect square that is its factor. So for example, 50 can be multiplied with the two numbers 2 and 25. So I can rewrite this as the square root of 25 multiplied by 2. And if you notice, this is a perfect square. And it's the largest one that's a factor of 50. And then by the rule that I just mentioned, I can rewrite this as 25 times square root of 25 times square root of 2. But luckily, the square root of 25 is 5. So the square root of 50 is equal to 5 rad 2. Let's look at other ones. How about the square root of 80? How can I break that down? So what are the factors of 80? Where one of the factors is a perfect square. The only one that's possible is 16 and 5. 16 times 5 is 80. 16 is a perfect square. But then I can break that down as the square root of 16 multiplied by the square root of 5. And what is the square root of 16? 4 rad 5. So I can break down the square roots if I find the highest perfect square that is a factor of that number. And I can break that down. And now 4 rad 5, for example, is the simplification of rad 80. So if I know that, what happens when I have this? No, pardon me. What happens when I have something like this? The square root of 2 times the square root of 50 plus square root of 98. Right now, I'm adding apples and oranges. I'm not adding the same thing. So what I have to do is I have to see, can I break each of these down individually? Well, I already found that the square root of 50 was what? 5 rad 2? So I can rewrite this as 2 multiplied by 5 rad 2. But then what's the square root of 98? How can I break down the square root of 98 with two factors where one of them is a perfect square? So you have to know the perfect squares. The perfect squares are 1, 4, 9, 16, 25, 36. And if you go to 49, 49 times 2, that gives me 98. And 49 is a perfect square. So this would be the square root of 49 multiplied by square root of 2. The square root of 49 is 7 rad 2. So look what I got. I got plus 7 rad 2. Now, whenever you multiply a number with a radical, you just multiply the numbers on the outside, because it's like saying 2 times 5 rad 2 is like saying 5 rad 2 plus 5 rad 2. It's like saying I'm adding 5 apples and I'm adding another 5 apples, right? So I have a total of 10. 10 rad 2 plus 7 rad 2. But now look what you notice. Now these are like terms. Like terms because they have the same radicand. You would say these are unlike terms because radicands are not the same. So now I'm saying what? I'm saying 10 rad 2s plus 7 rad 2s. How many total rad 2s do I have? In this case, I'm just going to add the coefficients, the number in front. I get 17 rad 2s. I don't add the number underneath the radicals. This works similarly the way we do 10x plus 7x, right? We just add 17x. It's similar in the way we treat it. So it's like saying we have 10 oranges plus 7 oranges. It's a total of 17 oranges. So that's how we treat radicals when we want to combine them. Okay. So far, right? This is what we've been really dealing with. Radicals, fractional exponents, knowing how to simplify radicals that are whole numbers. But what if now our radicals, well, actually I haven't completely done all of this. What if I have what if I have something like the cube root of 16, for example? How do I break this down? How do I break this down? So you see how it's a little different from the previous examples? The previous examples, we have square roots, square roots, square roots. Now I have the cube root. Now, 16 is not a perfect cube. I care about perfect cubes whenever I have cube roots. I care about perfect cubes. But 16 is not a perfect cube. So what do I do here? I have to try to find two numbers that is a perfect cube that multiplies to 16. So now I have to worry about my perfect cubes. What are my perfect cubes? 1, 8, right? 2 cubed is 8. 3 cubed is 27. 4 cubed is 64. So those are the perfect cubes. Now 16 can only be rewritten as what? As 8 times 2, where 8 is a perfect cube. This is not a perfect cube. This is a perfect cube. Do you see that? And now this becomes the cube root of 8 multiplied by the cube root of 2. 2 is not a perfect cube, so I just leave it. I leave cube root of 2 the way it is. The same way I left rad 2 because 2 is not a perfect cube anymore. But, or perfect square in this case. But the cube root of 8, I know what it is. It's 2. So the cube root of 16 can be simplified as 2 times the cube root of 2. Let me give you another one. Let me see. So for example, if I do the cube root of 40, I can rewrite this as the cube root of 8 multiplied by 5. 8 is a perfect cube again. But 5 is not. So I can't break down 5 any further. But I can break down the cube root of 8. And I get 2 cube root of 5. That's what the cube root of 40 simplifies to. And we can do this for other indices, right? I can do this for the fourth root. And the idea is I want to find the perfect whatever that index is. So if I have square roots, I want to find the perfect square. If I have cube roots, I want to find the perfect cube. If I have fourth roots, I want to find the number that has a perfect to the fourth power. And so on and so forth. Now, the problem, I think the most complicated of all this stuff is what's going to follow from here on out. So the problem is when we simplify the following kind of expression. If I want to break down, for example, the square root of x to the fourth times y cubed times z to the fifth. So this is an example. So when I take the square root of this product, I can also write this as the square root of x to the fourth times the square root of y cubed times the square root of z to the fifth, correct? I can do this. What I noticed though is that this is a even number, 4. And the number out in front here is a 2. So if you notice, I can rewrite this as x to the 4 divided by 2. I can rewrite it as a fractional exponent. And 4 divided by 2 is 2. So the square root of x to the fourth is x squared. The square root of x to the fourth is x squared. Now the problem arises when I have something like this. What in the world, so I'm going to put a little star here. What in the world does y cubed, what does that simplify to? How do we even approach this? Obviously, if I try to do the same thing that I did here, it wouldn't work because 3 cannot be divided by 2 evenly. I would have another fraction. I'll have y 3 halves. I don't want that. So what do I do? I know it's kind of difficult to interpret it this way, but think of y cubed, think of this number here as one of these numbers, right? Where you can't have, where it's not a perfect square. So technically, x to the fourth is a perfect square. But y cubed is not a perfect square. Because when you divide the exponent by 2, it doesn't just nicely evenly divide. So what are we supposed to do here? We're going to do the exact, very similar thing. We're going to try to find two numbers, or in this case, two variable expressions, where one of them is a perfect square. And we want to find the largest perfect square. That's a factor of y cubed. And the largest one happens to be y squared. If I take this and I take the square root of that, right? You notice this is a perfect square because I'm raising to the squared. I'm raising it to the second power. This is not a perfect square. So I take the square root of a perfect square. The square root of y squared is y. But the square root of y is just the square root of y. So the square root of y cubed is equal to y times the square root of y. I know. It's weird. But that's what it is. Now, let's look at the double star, the square root of z to the fifth. Again, this is the hardest part of this whole thing. This is it. So it may take some more practice with this. Z to the fifth power, I want to break that down. Z to the fifth, obviously, the fifth power is not divisible by 2, so henceforth, I'm going to have another fraction if I do that. So it's not a perfect square. So now I have to break this down into a product of two things where one of them is a perfect square. And what is a perfect square are the even powers. So make that another note. Note, variable expressions with even powers are perfect squares. Why is that? Well, because they're even, I can always divide the even power by 2, because that's what really is happening when I take the square root. You can think of it as dividing the exponent by 2 when you take the square root. So if they have even powers, they're all divisible by 2. So henceforth, I have a perfect square. So that means I want to find what factor smaller than z to the fifth is a perfect square. And the only way that's possible, or one way that's possible, is that z is being raised to the fourth power multiplied by z to the first power. Z to the fourth power is a perfect square because the exponent is a perfect square, is even divisible by 2. This is not a perfect square. So then we'll look what I get. I get the square root of z to the fourth of a perfect square multiplied by z to the first. Square root of z is just square root of z. But the square root of z to the fourth, remember we did this already? This is like saying z to the 4 to the 1/2 power times the square root of z. But then 4 to the 1/2 power, I multiply 4 times a half and I get 2. So this becomes multiplied by z squared rad z. Now, what do I do now that I've split each of these things down and I can't break it down any further? So what I do is I put everything that's outside the radical, I just put it in front. So x squared is outside the radical, y is outside the radical, and z squared is outside the radical. And everything that's inside the radical, leave it altogether inside. Y is inside, z is inside. And this strange thing is the simplification of our original radical expression. I know this may take some time to really apprehend what's happening, but the steps here will never change. It will be very systematic in this manner. So let's do a few more of these. So any questions? Any questions about this? Is this okay or not okay? Well, it looks like this is going to be a lot more practice that's needed, right? All right, so let's look at this, something like this. Square root of 60 x y to the 7th z to the 12th power. What I'm going to do is I'm going to take each of these individually. Take the square root of 60, take the square root of x, take the square root of y to the 7th, take the square root of z to the 12th. And I'm going to break down each of these individually. So square root of 60. Can I break down the square root of 60 as a product of two numbers? So what two numbers multiply to 60 where one of them is a perfect square? Does anybody know the factors of 60 where one of them is a perfect square? Anybody? Perfect squares, 1, 4, 9. Does 9 divide 60? No. 16 divide 60? No. 25 divided by 60? No. 36? No. 49? No. Too much, right? So the only number that exists that's a factor of 60 is 4. 4 goes into 60 15 times. 4 is a perfect square. Square root of 4 multiplied by square root of 15. What's the square root of 4? It's 2. 2 rad 15. So I know how to break down rad 60. Rad x. Can I break down x any further? I can't. It's just raised to the first power. So I can skip rad x. I can't break down rad x any further. Can I break down rad y? 7 to the 7th, y to the 7th. Remember, I want to find the largest perfect square. The largest perfect square is y to the 6th. It's an even exponent. Y to the 6th times y to the first power gives me y to the first. So I can break down y to the 6th multiplied by the square root of y. And what is the square root of y to the 6th? Well, the same thing as taking 6 divided by 2, and I get y cubed, square root of y. So I can break down y cubed. I mean y to the 7th. And then lastly, what is z to the 12th square root of that? Well, we're in luck that 12 is an even power. Since it's an even exponent, and I take the square root of an even exponent, the square root, there's really a 2 here, so I can rewrite this as z to the 12th raised to the 1/2 power, which really means I'm just taking 12 and dividing it by 2, so I get z to the 6th. So if I break this all down individually, I get what? I get 2 rad 15 times the square root of x times y cubed times y, rad y, multiplied by z to the 6th. So remember, this is multiplication, so I can rearrange the order of the operations. So I'm going to put all the ones that have no radicals in front in the left to the left. So 2y cubed and z to the 6th. So all of these are placed in front. And then everything that's underneath the radical, I'm going to put them all together. I'm just going to bunch them all up. So I got 15, I got x, and I got y. This becomes 15xy. And I have finished the simplification of my original example here. The square root of 60x y to the 7th z to the 12th, that reduces to 2y cubed z to the 6th power square root of 15xy. It's not pretty. It really isn't. But that's how you simplify it. All right, let's do one last one and we'll call it a day for today. So I'll give you now, instead of square roots, I'm going to give you cube roots. So for example, how do you break down the cube root of 8 of a to the 8th power, b to the 11th power, and c to the 15th power? So what I could do is I can take the cube root individually, and I'm going to break down each of these as I try individually to do so. So in this case, I want to find the perfect cube, the largest perfect cube. Now, if you notice from the previous example, right, if you have an even power, you can divide by 2 because I have the index of the radical is 2. In this case, I don't want it to be divisible by 2. I want it to be divisible by 3. So this is not a multiple of 3. So it's not divisible by 3, right? Not divisible by 3. So then what you have to do is find a number smaller than 8 that's divisible by 3. What's the largest number smaller than 8 that's divisible by 3? And it's to the 6th power. So this is not divisible by 3. But this is divisible by 3. So I can rewrite this as the cube root of a to the 6th times the cube root of a squared. Now, what's the cube root of a to the 6th? I can write this as a to the 6th raised to the 1/3 power. And I get this is a squared because 6 times 1/3 is 2. So a squared times the cube root of a squared. So yeah, I won't go into this all the way because I know we have time is up here. So we'll finish this one next time. So again, this takes a lot more practice. This is to be continued, okay? So this takes a lot of practice, but eventually with enough practice, you all should be able to get it.